we we started off last lecture with some discussion on problems relating to distribution graphs, and we continued with uh, a few other general unit hydrograph problems. So just a quick recap of the distribution graph idea. The concept of a distribution graph is based on finding out the percentage of volume of runoff contributed by every time interval as a percentage of the total runoff produced by a certain hydrograph, right? So I have a rainfall event. It produces runoff which lasts for, let's say, X number of hours. Now that X number of hours is broken up into intervals, and in each interval, equally spaced interval, we find out what is the contribution of that interval to the overall runoff, right? So for example, if it is from 0 to 8 days or 9 days, whatever it is, right? So in those 9 days, every 24-hour interval contributes some portion of the total runoff. Okay. When I say runoff, I mean the volume of runoff. Okay. So I compute the total volume of runoff produced by that particular rainfall event. And then I figure out the percentage that each day, now in this case, I'm saying 24 hours, it could be any duration, right? It could be a 60-hour duration, which I break it up into 5-hour intervals or whatever it may be, right? So the distribution graph simply gives us the percentage contribution from each time interval over the entire duration of the runoff that is being produced. Okay, so we solved a couple of problems relating to this distribution graph idea, and then we moved on to solving this particular problem. Again, straightforward one. The only challenge or only difficulty in this particular problem that we looked at was that the spacing between the successive time intervals is not uniform throughout the entire duration. So I have time from 0 to 138 hours, but it doesn't go in equal steps. And therefore, if you have to lag this hydrograph to add multiple hydrographs, then it becomes a challenge, right? Because you have to maintain the time difference between each successive time. Here you have to maintain that difference, so then it becomes a challenge to lag these kinds of hydrographs. That is the only difficulty in this particular problem. It was not required, because you just take this hydrograph and divide it by the excess rainfall. That gives you the unit hydrograph, but it would be a unit hydrograph which does not have equally spaced time intervals, which, as I said, is not convenient, but it's not a problem. Okay, all right, we'll just do 2 more problems and then we'll move on to just the final discussion for the day. Okay, all right. So the 3R unit hydrograph for a basin has the following ordinates. Using the S-curve method, determine the 9-hour unit hydrograph ordinates of the basin, right? So now immediately, as soon as you read this problem statement, you understand something, which is that in this particular problem, you have been asked to use the S-curve method, although the time difference, the time durations that are given, what you're provided is a 3-hour unit hydrograph, and what you're asked to do is to produce a 9-hour unit hydrograph. Now, this is an integer multiple, but still you have been asked to use the S-curve method. As you remember, if you have a integer multiple, it is perfectly straightforward and perfectly correct if you use the method of superposition. There is nothing wrong with it. It will give you the right answer. It will be the correct answer. It will be identical to whatever you get with the other method. But in this particular example, you have been asked to do it a particular way, and therefore you just have to follow the instructions, basically. Okay, so we will just walk through the steps. Okay, all of you are familiar with this S-curve approach, but we'll just walk through the steps. Okay, and time goes from 0 to 60 hours. Okay, but I'm not going to show all 60. I didn't have space to fit. I had space to fit up to 42 hours. But the procedure is the same, so you know what to do. Okay, so I have time from 0 to 42. Let's assume that it ends at 42, but for this purpose. So now, what is the first thing that I have to do? First thing I have to do is to construct the S-curve. Okay, So how do I go about constructing the S curve? It's straightforward. You first fill in the S curve addition column, and then you have the S curve ordinate column. At time t equal to 0, the S curve ordinate will be 0. And after that, you just keep populating this addition column, and then you get the uh, uh, S curve column itself, right? So I've just computed all these numbers. I'm just showing you. Don't worry about it. I'll share these slides. You can always, you don't have to note all these numbers down. Okay. So what have I done? All I've done is taken the first row. Second. For some reason this, no. The first row is straightforward. Okay, there it is. So you just get the 0. And after this, you just keep populating the column number 3 with the value in column number 4, but you just have to go one row above. Okay. So then 12 plus 0, 12, right? So this is 12 plus 0, and you get this number 12. And then this 12 again comes down, 75 plus 12, 87. And then 87 comes down here, and then 132 plus 87, 219, and so on. Right. So this, you have to keep doing this for the 60 hours that is being given. I have shown here computation up to 42 hours, but the procedure remains the same, right? So you just compute this number, bring it down to the next row, right? Straightforward idea. You just have to implement this. Of course, in this case, you've been given so many numbers. There is nothing fundamentally difficult about it. It's just laborious. Okay. All right. So after I've done this, what should I do next? Once I've got the S3 curve, now you'll notice that in the fourth column, I have mentioned it as S3. There's a subscript there which says 3. What does that 3 signify? Anybody? What does the 3 signify? What does the 3 signify? Please, quickly. Okay, Dharvika, what does the 3 signify?
3-hour unit hydro.
Correct. It is an S curve produced from a 3-hour unit hydrograph, right? So in general, SD, if I put D there, that D denotes that it is an S curve constructed from a D-hour unit hydrograph. Okay. So in this case, it's a 3-hour unit hydrograph. So I say S3. Okay. Yeah. Sriram, what should I do next?
Lagging by that time gap we required.
How many hours is it? We require a 9-hour unit hydrograph, right? So we should lag it by
9 hours.
9 hours. Thank you very much. So the S3 curve lagged by 9 hours. So you will see that at 9 hours, it has got the value 0, which means it's starting from there at the time t equal to 9 hours. Sorry. Yeah, this is the starting point. So this is time at time t equal to 9. I start off with 0, and then it goes 12, 87, 219. Whatever is in the column number 4, I brought it to column number 5, except that it is starting from time t equal to 9 hours. That is the starting point. What should I do next? Yeah, Venkatesh, what should I do next?
So we will add up both.
Say that again.
We will add up them.
Add.
And we have to divide them by 3.
Wait. But let's go one step before that. Should we add them or subtract them?
Sorry, sir, subtract them.
Subtract them, right? So why are we subtracting them? Because the first S curve is produced by a excess rainfall intensity of 1/3 centimeters per hour occurring for an infinite amount of time. The second S curve, which is lagged by 9 hours, is also is a hydrograph produced by 1/3 centimeters per hour of excess rain occurring for an infinite time starting at time t equal to 9 hours. So when I subtract them, the hydrograph that I get is a direct runoff hydrograph produced by 9 hours of rainfall, 9 hours of excess rainfall of amount. When I subtract the two S curves, I will get an excess rain. I'll get a direct runoff hydrograph produced by 1/3 centimeters per hour of excess rain happening for 9 hours. right? Because when I subtract them, uh, uh, starting from time t equal to 9, the rainfall intensities will be the same. So when I subtract the two, those excess rainfall intensities cancel each other out. I'm left with excess rainfall of intensity 1 by 3 centimeters per hour happening for 9 hours, which means 1 by 3 into 9 hours is 3 centimeters. So what I get when I subtract column, so it's when I do column 1, 2, 3, 4 minus column 5. I subtract column 5 from column 4. I get 0, 12 minus 0, 87 minus 0, 219 minus 0. Up to that time, it's all the same as column number 4. Then 319 minus 12, 609 minus 87, and so on. I get the direct runoff hydrograph. Again, I have not taken this all the way down to 0. I've stopped at time t equal to 42 hours. But if you are solving this, you would actually extend it all the way to time t equal to 60 hours or whatever it is mentioned in the problem. Okay. So now the important thing here is that the title of that column number 6 that you have there, it has 3 important things. Number 1, the duration of the direct runoff hydrograph. It is a direct runoff hydrograph of 9-hour duration, right? Because when I subtract the two, I'm left with rainfall of duration 9 hours. So that's point number 1. The second thing is that it is a direct runoff hydrograph. It is not a unit hydrograph, right? And the third point that is there is that this was produced by excess rainfall ER of 3 centimeters, right? So that simple title on that 6th column has so much information packed in it. Okay, it is mentioning the duration of the hydrograph, it is mentioning the type of the hydrograph, and it is also mentioning the quantity of excess rainfall that produced that hydrograph, right? So you may think it's a minor point, but it is conveying so much there. Just those few words are conveying so much information there, right? In fact, all of the titles that you see here, all of them have got a lot of meaning, right? So it is important when you're solving an S-curve problem of this nature to mention clearly what you're getting in that particular column right in the title itself, because then there's no confusion about whether you've calculated this or that or right. So in fact, what I would say is more important than all the numbers that you're populating inside this table is the titles of the columns. Because if you show that the title is correct, right, that means you've understood the concept. While computing the 609 minus 87, you can always make a mistake. Instead of 522, you may write 532, whatever it is. That's an insignificant detail in my opinion. That's just a number, right? But the column heading actually tells me that you've understood what you're doing, right? The numbers are incidental, right? It's totally possible to make a mistake in these numbers, but the column heading is more important than the numbers themselves. Okay, so this I think is, I hope, I mean, of course, there's only the 3 of, how many of you are there? Only the 3 of you, 4 of you. So Raymond is also here, sorry. So just the 4 of you here, but I hope that this point is kind of made crystal clear to everybody. Of course, assuming everybody watches this video, please pay attention to the column headings more than the numbers that you put in there. The numbers, anybody can make a mistake. It's not a big deal. But the column headings tell the story more than the problem itself. Okay. All right. So now we have come to the final step. Okay. So Revant, in case you missed the problem statement, let me just quickly go back. I'll describe what the problem is. So a unit hydrograph is given, a 3-hour unit hydrograph is given. You are asked to use the S-curve method to determine the 9-hour unit hydrograph for this particular basin or this particular watershed. Okay. So in this case, although it is a integer multiple, right? I have a 3-hour unit hydrograph. I'm asked to produce a 9-hour unit hydrograph. Now, between 3 and 9, of course, it's a integer multiple, right? I can just use the method of superposition. Take this unit hydrograph, lag it once, lag it twice, add them up, divide by 3. That will give me the answer for the 9-hour unit hydrograph. But because this problem statement asks us to use the S-curve method, we are doing this S-curve method. Okay, so there's nothing wrong if it's not mentioned. If it is just asked to find the 9-hour unit hydrograph, it is perfectly legitimate to just directly use method of superposition. It's obviously probably conceptually simpler than the S-curve method. Okay, But anyway, it's not rocket science. Okay, not at all hard. Anyway, so that's where we were at, and then we constructed the S curve, lagged it by 9 hours, and then subtracted the two from each other, and we've got the 9-hour direct runoff hydrograph produced by excess rainfall of 3 centimeters. Okay, so Revant, last step, what should we do next? What we want?
Add them.
Say that again.
Add them.
Add what?
9 hour unit.
No, add what to it? Okay, so let's just think about what we want. We want a 9-hour unit hydrograph, which means we want a hydrograph produced by how many centimeters of excess rainfall?
9.
Unit hydrograph means how many centimeters of excess rainfall?
1 centimeter.
1 centimeter. The duration of the rainfall is 9 hours. In that 9 hours, 1 centimeter of excess rainfall has happened. Okay, that is what we want. What we want is a unit hydrograph. What I have here in column number 6 is a direct runoff hydrograph of the same duration that I want, 9 hours. But the amount of rainfall that produced this hydrograph is 3 centimeters, amount of excess rainfall. Okay, I want for 1 centimeter, I have for 3 centimeter. What should I do?
Add them and divide it by 3.
Add what? What do you mean by them?
3 centimeters. 9 hour duration excess rainfall.
Correct. We already have it, right? So column number 6 is the direct runoff hydrograph produced by 3 centimeters of excess rainfall happening in 9 hours. I want a unit hydrograph, which by definition is produced by excess rainfall of 1 centimeter happening in the same 9 hours. So what you said initially was correct. You have to divide it by
3.
3, right? So I just divide all the numbers in column number 6. I divide it by 3 and I populate the unit hydrograph in column number 7. Right? So that's all there is to it. As I said in the previous class also, this is a kind of a typical problem that is given as an exercise for the S curve method. Okay, very typical problem. Of course, this one has lots of numbers. I don't pay too much attention to the numbers, but the concept is more important than putting all these numbers correct. If you make one mistake in these calculations, that's not a big deal, right? But if you have all these columns here, there is no chance that there's no chance of a conceptual mistake. There may be a chance of a calculation mistake, but these columns indicate clarity in the concepts that are being discussed. Okay. All right. Shall I move on? Okay. I'll take that as a yes. Okay. Let's look at this. This is an interesting problem. Okay. The 6-hour unit hydrograph of a catchment is triangular in shape with a base width of 64 hours and a peak ordinate of 30 cubic meters per second. Calculate the equilibrium discharge of the S6 curve of the basin. Okay, so in case you've forgotten what an equilibrium discharge is, does anybody remember what equilibrium discharge is? Oh, sorry. So time on the x-axis and discharge on the y-axis. So the S curve looks something like this. It reaches some peak value and remains there. Now this peak value is called the equilibrium discharge. Let's call it QE. Okay. So the question is, what is QE? That's what the question is trying to is asking us to find out. Okay, take a couple of minutes and somebody tell me what we should do to figure it out. So this S curve is produced by 1 centimeter of excess rainfall happening in 6 hours, right? So it's 1 centimeter, 1 centimeter for infinite dot 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 dot, and just keep extending that. Each box represents 1 centimeter of excess rainfall happening in 6 hours, and like that I have an infinite number of boxes, stacked one after the other, no gaps in between. So I get continuous rainfall of 1 by 6, continuous excess rainfall, 1 by 6 centimeters per hour of excess rainfall happening for an infinite time produces this curve. And the question is, what is the magnitude QE? What height will it go up? Okay. Anybody has a thought on this? We spoke about this probably 2 lectures back. Anybody remembers? Okay, I will just mention what I'm going to do is I'm going to take this rectangle here, because once it reaches that value of QE, it never goes down. Okay, I'm going to take a rectangle there of width 1 hour. Okay, so I have QE, the ordinate on the y-axis, right? And then I'm taking a delta t of 1 hour. So the area of that rectangle will be QE into 1 hour, correct? Of course, you have to convert it to meter cube per second. So 1 hour, you have to convert it to 3,600. Does everybody agree with me? QE, meter cube per second, into 1 hour into 3,600 seconds per hour. So you will have the area of this area there will be QE into 3,600 meter cube. Right, so QE into 3,600. This is the volume of runoff, produced. Okay, this must be equal to, how can I find the volume of runoff produced in that 1 hour? So the excess rainfall intensity, what is the excess rainfall intensity that produced this S curve? Okay, since there's only a few of you, I'll have to go back to you and ask you the same names. Oh, Puneet is here. Okay, so I have a few more people. Puneet, what is the excess rainfall intensity that produced this hydrograph? It's okay if their answer is not correct. Okay, just go ahead and give me an answer. Or just unmute yourself. Let's walk through it. I'll ask a different question then. Puneet? Come on. You're in the mess, you're having breakfast and then listening to the class, so it's too noisy, so you don't want to unmute yourself. Something like that, I assume. Okay. Okay, back to Sriram. Okay, Sriram.
Area of the triangle we can use, I think.
No. Listen to the question. Just tell me. The question is, what is the excess rainfall intensity that produced this S curve?
1 by 6 centimeter per hour.
1 by 6 centimeters per hour. Now I have taken a 1 hour interval and found the area under that curve, between in that duration of 1 hour. I found out that the amount of runoff will be QE into 3,600. Correct?
Yes, sir.
Now my question is, can I equate this in that 1 hour? How much excess rainfall would have happened? The intensity is 1 by 6 centimeters per hour, correct? And the duration is 1 hour. So how many centimeters of excess rainfall would have happened in that 1 hour?
1/6 centimeter.
1/6 centimeters, correct? So in general, I can say 1 by d. 1 by d centimeters of excess rainfall would have happened in that 1 hour duration, correct?
Yes, sir.
In this particular case, d is 6, but if I want to generalize it, I will say it is 1 by d centimeters. And the area of the catchment is, let us say it is a kilometer square, correct?
Yes, sir.
So this left hand side is QE into 3600 meter cube. That must be equal to a kilometer square into 1 by d centimeters. Of course, converting it to meter cube. Everybody agrees with me? Okay, so it will be on the right hand side, I should have a kilometer square into 10 to the power 6 meter square into 1 by d centimeter. So that will be 1 by d into 100 to get it in meters. So this whole thing, if I multiply it, I'll get a into 10 to the power 4 by d meter cube. So which means QE equal to, so if I rearrange this, I'll get QE equal to 10 to the power 4, because 10 power 6, there's a 100 in the denominator, that becomes 10 power 4 divided by 3600 into a by d. Right? A will be in kilometer square and d will be in centimeters, because I've already applied the conversion 10 power 6, 100, all of that. Right? What is 10 power 4 divided by 3600? Somebody quickly give me. Yeah, Sriram, quickly. 10,000 divided by 3600.
2.77.
2.77, 2.78, I think. Huh? Something like that.
Yes.
2.778. So this is the equation for finding out the equilibrium discharge. 2.78 into A. Now remember, this A has to be in kilometer square, and D has to be in hours, right? Because I've already taken care. It has to be in hours. Okay, so I've already taken care of the conversions and all of that, because I've put in that equation 10 power 6 meter square to convert from kilometer square to meter square, and to convert D, which is in 1 by d, which is centimeters per hour, to convert it to meters per hour, I've already divided by 100. So the conversions are all taken care of. This is a simple equation that gives me the equilibrium discharge for a given basin. Now the point is, I know d in this equation. D is 6 hours, but I don't know the area of the catchment. Now, how do I find the area of the catchment? So that's what you were trying to answer, Sriram. I remember. Okay. But let's, Venkatesh, how do I find this A now? Or Puneet, anyone? Let's finish this quickly. Okay, so the area of the catchment you will find by finding the area of the triangle, which is the unit hydrograph. You will use the same approach. You will equate the area of the triangle, which is half into base into height. Of course, after converting it to seconds, I mean hours to seconds, you will get meter cube. That must be equal to area of the catchment into how many centimeters of excess rainfall? So the area of the triangle gives me the volume of runoff. Now the volume of runoff must be equal to the area of the catchment into the centimeters of excess rainfall. How many centimeters of excess rainfall produce the unit hydrograph? 1 centimeter. Okay, this blur video doesn't show my hand properly. Okay, so 1 centimeter of excess rainfall produced the unit hydrograph. So therefore, I can compute the volume of runoff produced by 1 centimeter of excess rainfall by multiplying A, the area of the catchment, with 1 centimeter, and then equating that with the area of the triangle. Now I know the dimensions of the triangle. The base is given 64 hours. The peak is given 30 meter cube per second. So I find the area of the triangle equated to this, and I don't know the area of the catchment. I find out A. Once I get A from there, I put it into this equation and I get the equilibrium discharge of this basin. Okay, so that's what we are going to do. So I'll erase all of this that I've written here, and it's a lot of stuff. Oh, I think there's an option to just erase all ink on slide. Simpler. Okay, nice. So now, so calculate the area under the 6R unit hydrograph. So it's half into 30, the peak height into 64, that's the duration, into 3600 to convert to hours, meter cube. So I get the area under the unit hydrograph, 3.456 into 10 power 6 meter cube. That's the volume of runoff produced. Now I equate this with the area of the catchment by dividing it by the duration, by the amount of excess rainfall. That's 1 centimeter, which is 0.01 meters. So that gives me 345.6 kilometers square. Okay. Now I have everything that is required to find out the equilibrium discharge, which is given by 2.78 into A by D, which comes to around 160 cubic meters per second. Okay. So remember, A will have to be in kilometer square and D will have to be in hours. So I just put 2.78 into 345.6. You don't have to convert it to meter square or anything. That is already taken care of in that 2.78. And D will be in hours, which is 6. Again, you don't have to convert it to seconds. Just put those numbers in, you get the equilibrium discharge, 160 cubic meters per second. Any questions? Okay, so there's no questions. We will just move on to the next, I won't say topic, it's the next project that we are going to have to do. Okay, so what we're going to do, the next project is, each group is going to design a storm sewer for a college campus, right? Just like we have on our campus, there are those streams, open channels that have been constructed all over the campus, right? You have seen them. Whenever there's a rainfall event, you will see water flowing down those channels towards the lakes, right? So those channels have been designed for a certain kind of rainfall event. So you are going to be designing a storm sewer for a college campus. What I want each group to do is to pick a different district in Andhra Pradesh. Okay, each group will pick one district in Andhra Pradesh, and you will assume that the size of your campus is approximately around 500 acres. Okay, similar to our campus. Okay, because the amount of runoff produced by the campus depends on the size of the campus, right? So depending on the size of the campus, I mean, it doesn't have to be exactly 500. It can be maybe 600, 450, something like that. So just pick, you will have to pick a district, and you have to pick a location inside the district, which is of size approximately 500 acres. Okay, so this is the task that you will do. Now, picking this location of the campus is going to be something that will be an interesting exercise. Okay, so the data that you will be provided to do this project is that you are going to be provided the land use map for Andhra Pradesh. I'll show you what the land use map looks like. Okay, and then you'll also be provided the precipitation data. You will also have the topography information. Topography is basically how the land surface changes as a function of space. So it's called a digital elevation model, DEM. Okay, and then soil type information, of course, is available online for each district or each part of Andhra Pradesh. You have the soil type data available, right? So using all this information, you will try to find out, okay, so what is a good way of figuring out the size of a storm sewer in a particular location? What are the factors on which this size of this storm sewer will depend on? Anybody? It will depend on the peak amount of runoff that is going to be produced by this campus, right? The amount of runoff produced by this campus determines the size of that storm sewer, right? When I say storm sewer, I mean you will have to decide whether it is going to be a trapezoidal cross section or a rectangular cross section or some other cross section that you want to decide. Okay. For example, on our campus, you will notice that the cross section is trapezoidal in shape. So it is your decision whether to go for a trapezoidal shape or a rectangular shape. Trapezoidal, generally speaking, is easier to construct. Okay, and it can be made with rocks and gravel that we have used on campus that has been used to make the storm sewer network inside our campus has been made with the rocks that have been available on campus, right? And therefore they've used a trapezoidal shape. But if you are going to use concrete lining, okay, then it's easier to do a rectangular shape. I mean, concrete, any shape can be done. Rectangle is of course easier to do, and in terms of, it will also minimize the cross-sectional area and so on and so forth. Okay, so I'll leave that decision to you. Whether you want to use concrete or you want to use natural earthen material is something that I will leave to you. So number one, the point is the amount of runoff produced is going to determine the size of your storm sewer. Okay, now which runoff should you look at? Should you look at the average runoff that is produced by your campus, or what else? What should be the factor that determines this? So you will need to decide based on the peak runoff that will be produced by your campus, right? Whatever campus you are building. Now remember, the campus today, when you pick the location, it might have a certain type of land use. Okay, but once it's finished, the campus is construction is finished, it will have more built up area, more urbanized area, more parking lots, more buildings, and so on. So you have to not plan for today's land use. You will have to plan for land use after the campus is completed, right? That makes sense. So let's say you have a campus of 500 acres. Out of that, some portion of it is going to become constructed area, right? So for example, if you look at the older IITs, you can go on Google Maps, look at the older IITs, you know the boundary of the campus, you can find out how much of that area has become constructed, right? Just by looking at it, you can see there will be some playgrounds, there will be some forested area. Usually most of our IITs have some kind of a forested portion inside the campus. You may have some open areas, you may have grounds, open air theaters, all of these things, which most likely will have natural soil. So they will remain more or less undisturbed from before. But then you'll also have roads, you'll have parking areas, you'll have buildings, and so on and so forth. So using data from the older IITs, all of which are available on Google Maps, you can just zoom into IIT Bombay, IIT Madras, IIT Kanpur, Kharagpur, and so on, and find out what percentage of their campus is constructed area and what percentage of it is natural land surface. Okay, so you can assume some kind of similar percentages for this campus that you're going to be constructing in some part of Andhra Pradesh, and accordingly figure out how much runoff will be produced. So you can use, I'll leave it to you, but to find the peak runoff, which method is better? Anybody remembers? You can use of course, there are two methods that you could use. One would be our soil SCS curve number method. That's a possibility. You can decide whether you want to do that. Or you can use the rational method, Q equal to CIA, right? Where C is my runoff coefficient, I is the peak rainfall intensity, and A is the area of the campus, and so on. So if you have 500 acres, you divide it into different zones: residential zone, 10 acres or 20 acres, whatever it is; hostel zone, 15 acres; academic zone, something; natural land surface is probably 200 acres, something like that. So you divide it all up, and then for each area, you will have a different curve number or a different, or a different runoff coefficient. And accordingly, you will find out how much runoff will be produced by each. You add them all up, that gives me the peak total runoff that is being produced by that particular campus. And once you have that peak runoff rate, so it should be in units of meter cube per second, right? So decide which method you need to use if you want units of meter cube per second. Okay. And then once you have that, you will use Manning's equation. Remember Manning's equation. So it will help you to, in case you don't remember, Manning's equation is something like this: Q equal to 1 by N A R to the power 2 by 3 S naught power half. Now, N is the Manning's coefficient that depends on the material that is being used for constructing the uh, uh, the storm sewer. A is the area of cross section through which the flow is happening in that particular storm sewer. R is the hydraulic radius A by P, you might remember, and S naught is the bed slope of that campus. Now, how do you get bed slope? You will have to use the topography of that particular region. Now, when you pick the location 500 acres, you might have different slopes in different parts of the campus. So you will have to pick the steepest slope somewhere in the campus to find out where will be the slope be highest. So if you're or where will the slope be the least, and so on, right? When the slope is least, that's when the depth of water will be highest, when the water flows through the channel. When the slope is steep, then the depth of flow typically becomes lesser, right? You remember supercritical flow, subcritical flow, and so on, right? So you will be able to design the channel once you know Q. So in this equation, left-hand side Q will be known by using, let's say, rational method. You will find out what is the peak runoff rate. Okay, N will be based on the material that you are going to use. If you use concrete, you will have a certain value of Manning's roughness coefficient. If you're going to use earthen material, you know what the N is. S naught is determined by the topography of that particular region. Okay, A and R are the design parameters. A and R are dependent on the area of cross section. Now, if you decide to have a rectangular cross section, the geometry will be taken care of in A and R. Okay. Similarly, if you decide to use a trapezoidal cross section, A and R will vary accordingly. Okay. So that's what this particular project is going to be like. So I will leave it kind of as an open-ended task. Now, I will just mention one thing. Let me open QGIS. I'll stop sharing this. I'll open. Let me know if you can see QGIS right now. So we just have a couple of minutes left. I'll quickly wrap up, and then if you have questions, of course, you can email me. Okay, let me know if you're able to see the screen now. Yes, visible?
Yes, sir.
Okay, thank you. So this is the district map of Andhra Pradesh. This is the old districts, 13 districts. Right now, Andhra Pradesh is divided into 26 districts or something like that. But anyway, it doesn't matter. Okay, I'm going to show you the land use data for Chittoor district. Okay, so Chittoor district is where IIT Tirupati used to be. Of course, now it has become Tirupati district. But anyway, it doesn't really matter. We don't care about the geographic boundaries and all that. Okay, so now what this map is showing is the different types of land use in the different parts of Chittoor district. Now, can anybody guess what this red color indicates? Any guesses?
Populated area.
Urban areas, right? So wherever you see red, that is an urban area. So when you pick the location for your particular campus, obviously you can't pick it 500 acres, you can't pick which is in an existing urban area, right? Because it's already urbanized. Nobody is going to hand over their building to you to construct a new campus. So you will have to pick an area which is not red. Okay. Now I'll also give you some other hints for what to do. Now, if you zoom in further, in fact, you will notice. I just zoom in here. You will see there's this red area, and then there's a thin red line going through here. What do you think that is?
National highway.
National highways or any highway, basically. Okay. So you have in different parts, you will see these red lines. So you see, even on the left-hand side, you see there's a red line going here. So that's basically a highway. So when you pick your location, 500 acres, try to pick it as close as possible to a highway, right? So for example, even our campus right now, it's right next to the highway, right? You don't want to pick your 500 acres in the middle of very far away from an existing highway, because then accessibility is a problem. And this dark green color that you see, that's a forest. So you don't want to pick a location that's in the middle of the forest either. Okay, so try to pick a location which is close enough to some area, which is not very far from highway, and also which is not in the middle of a forest. Okay, I'll share one more screen with you. I'm going to stop in the next 2 minutes. Just bear with me. Let me know if you can see this. Are you able to see this? So this this gives you the different land use types for the different colors that are seen on the map. Okay, so when you click on a particular location, it will tell you what is the value. So the values go from 1 to 18. Okay, so the land use value will either be 1, 2, 3, 4, or 18. So try to pick a location which is not in the middle of a forest. So for example, number 8 is evergreen forest, or number 9 is deciduous forest. So you don't want to pick a location which is in the middle of a forest. Okay, it can be on the adjacent to a forest, like we have right now on our campus. We are right next to the forest, next to the hill. Okay, so pick your 500 acres carefully. Also, don't pick an area which is existing water body. You don't want your entire campus to be a water body. Then you'll have flooding issues and so on. So be careful while picking out this area. And then once you picked out the area, project what the land use will be in the future, and then figure out what the runoff coefficients will be in the future using some tables that are available. And then plan for what kind of rainfall event you would like to predict for the future. Will you use a rainfall event that happens once in 5 years, or once in 10 years, or once in 50 years, or once in 1,000 years, right? The more rare the event, the larger your cross section becomes. So you want to optimize it in such a way that you reduce the cost of construction. You don't want to construct it such that it will happen, it will get flooded, your storm sewer will overflow every 2 years. That would be too much savings on initial cost and too much expenses on maintenance and so on, right? Because your your channel will overflow and it will cause flooding and so on and so forth. But if you build something that is for once in 1,000 years, it will be such a huge cross section that you will never get flooded, but the cost of construction will be very high. So you will have to pick a balance. Maybe once in 50 years would be a good balance to pick. Okay, so that's the project. I will discuss with Roshan and decide when to make it due. Okay, and then it might be due, let's say, in 2 weeks from now, 3 weeks from now, something like that. And I'll let you know when it is due. Okay. So that's it, guys. We are done for the day. We are done for the semester with me. That is. All the very best to each one of you. I will continue to be accessible by email. You can send me messages on WhatsApp if you have any doubts, and so on and so forth. All the very best for everything. Take care of yourselves, and yeah, let's be in touch. I just hope everybody has a successful semester, rest of the semester, and let's hope that everything goes well. Okay, thank you so much for being here today and with me for the rest of the semester. I will continue to be accessible by email or WhatsApp. Please let me know if you have any doubts on whatever we have done so far, any topic that we have covered so far. Okay, thank you so much, guys. Take care and see you soon. I'm going to be leaving in a couple of days. Sunday night I'll be leaving for Canada. So that's it. Take care, everybody. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you,
Sir,
guys.
how was your celebration at IIT Madras?
Sorry, say that again.
How was your Dasra celebration at IIT Madras?
I'm not able to hear you.
IIT Madras celebrations.
Okay.
Yesterday you went to IIT Madras, right? He's asking about-
I didn't go to IIT Madras. I was some of my students visited me. They visited me at my house, and 3 of them are at IIT Madras. Maybe more, but at least 3 of them visited me, and we had lunch outside. And then, yeah. Thank you.
Sir, you saw your picture.
I know. You guys are not totally clued in on that. I don't know. I don't have anybody's WhatsApp numbers, or even if I do, I don't check their status. What is that status message thing that comes? I usually don't check that. I don't know why. But so I don't know if even if they post something on their status, I don't see it. I'm not used to seeing that. But I heard that some people already called me and said, "Hey, we know that you went to IIT Madras, or you met these people from IIT Madras." So yeah, I did have lunch yesterday with three of them. One of them he graduated 2 years back, Shivendra Gupta, and then Swastik Mishra and Sai Verma. They graduated this year, 2025. So all three of them are doing their MTech at IIT Madras. So yeah, they're all very going to be very successful, like all of you are also going to be. So yeah, let's hope for the best for everybody. Okay, thank you so much, guys. Take care. Bye.
Thank you, sir.
Thank you, everybody. Thank you, Puneet. Thank you, Sriram. Thank you, Revant. Thank you, Venkatesh.
Bye, sir.
Bye, bye,
Bye, sir.
bye, bye, bye.